Hello everyone. In this video we are going to look at binary heaps. But first, what is a heap? If we go by the definition, heap is a tree-based data structure that satisfies the heap property. A tree in computer science looks something like this. Now heap property states that for any parent P and any child C, the value at parent must be greater than or equal to the value at child for max heap, and the value at parent must be less than or equal to the value at child for a min heap. But we are not interested in a general heap here. We are interested in a binary heap. A binary heap has two constraints. 1. Binary heap should be a complete binary tree. 2. It should satisfy the heap property. Since we know what the heap property is, let's discuss what a complete binary tree is. A complete binary tree is a binary tree in which all the levels of the tree except possibly the last one are fully filled, and if the last level of the tree is not complete, the nodes of that level are filled from left to right. In other words, every level except the last level should be completely filled, and if the last level is not completely filled, it should be filled from left to right. So let's look at some examples and check if these trees are complete binary trees. In this tree, the penultimate level is fully filled and the last level is filled from left to right. So this is a complete binary tree. In this tree, the penultimate level is completely filled, but the last level is not filled from left to right as we don't have these nodes. So this is not a complete binary tree. In this tree, the penultimate level itself is not completely filled as we do not have this node. So this is not a complete binary tree. In this tree, the penultimate level is completely filled while the last level is not filled from left to right since we do not have these nodes. So this is not a complete binary tree. In this tree, the penultimate level is completely filled and the last level also is filled from left to right. So this is a complete binary tree. In this tree, all the levels are completely filled. The penultimate, the last level, all of them are completely filled. So this is a complete binary tree. In fact, this is a full binary tree as all the levels are completely filled. So we can say that a full binary tree is always a complete binary tree, while a complete binary tree may or may not be a full binary tree. Now let's check out if these complete binary trees are binary heaps or not. Remember the property of binary heaps that for any parent P and its child C, the value at P should be greater than equal to value at C, or the value at P should be less than or equal to value at C. This is for max heap and this is for min heap. In this tree, we can see that for node 12, both of its children have the values less than itself, and for the node 11, both of its children as well have the values less than itself. So this is a complete binary tree as well as a binary heap. And since for every node here, the value of its children is less than itself, this is a max heap. Now let's look at this tree. We can see that this node satisfies the property of a max heap because the value of its children is less than itself. Let's look at 11 now. We can see that this node, the node 13, is greater than 11. So this does not satisfy the property of a max or a min heap. So this is not a binary heap. Now let's look at this tree. We can see that for node 12, both of its children, which is 13 and 14, are greater than 12. So this satisfies P less than C. Let's come at 13. We can see that both of its children, that is 15 and 18, are greater than itself. So this also satisfies P less than C. And when we come at 14, we can see that both of its children, 21 and 22, satisfy the property that P is less than C. So all the nodes which have children satisfy the same property. So this is a binary heap. And since for every node P is less than C, we can say that this is a min heap. Now let's look at this tree. If we look at the node 4, we can see that both of its children 5 and 7 are greater than itself. So it satisfies the property P less than C. And when we come at 5, we can see that its only child is less than itself. So it satisfies the property P greater than C. Since these properties are not aligning in the whole tree, we can say that this is not a binary heap. Now let's look at this tree. If you observe carefully here, this is not even a complete binary tree because while the penultimate level is complete, the last level is not filled from left to right. So this is not a complete binary tree, and in turn, it's not a binary heap. Now let's look at this tree. If we look at the node 20, both of its children, that is 1 and 18, follow the property that P greater than C, And when we look at the node 1, both of its children follow the property that P is greater than equal to C. Since these two properties also align in the whole tree, we can say that this is a binary heap. And since P is greater than equal to C for the whole heap, we can say that this is a max heap. Just remember that the parent and child can have equal values. Now that we understand the properties of binary heaps, let's check out how they are represented or stored in a program. So they are stored in arrays where if the ith node is the parent, then 2 times I plus 1th node is the left child and 2 times I plus 2th node is the right child. Now let's understand this with an example. In this tree, since 12 is the root, it will go to the 0th index. So 12 will go here. Now let's look at the left child, which is 11, and it will go to the 2 times 0 plus 1th index, which is 1. So 11 will go here. Its right child is 10. So it will go to the 2 times 0 plus 2th index, which is 2. So 10 will go here. Now let's come back to 11. Its left child is 8. So it will go to the 2 times 1 plus 1th index. Since 11's index is 1, so 8 will go to 2 times 1 plus 1, which is 3. So 8 will go to the third index. Now let's look at the right child of 11, which is 9. It will go to the 2 times 1 plus 2th index, which is 4. So 9 will go here. Now let's look at the only child of 10. Since it's the left child, it should go to the 2 times index of 10, which is 2 plus 1th index. This is 5. So 7 will go at 5. Now, given the tree and the array representation, for any child at an index I, we can find its parent by following the formula I minus 1 by 2, and we need to floor the result. Let's look at an example. What will be the parent of 5? So we subtract 1 and divide it by 2 and get 2. And we can quickly verify that the node at 5 is 7 and node at 2 is 10. And in the tree as well, 7 is the child of 10. Let's look at another example. If we are given an index 4, how will we find the parent? We'll subtract 1 and divide by 2 and floor the result and we'll get 1. Now we can verify this as well. Node at 4 is 9 and node at 1 is 11. And when we look at the tree, the parent of 9 is definitely 11. So this checks out. Again, if we are given a node at index I, then we can find out its parent's index by using this formula, which is I minus 1 by 2, and we'll floor the result. So guys, this was the basics of binary heap. I hope you enjoyed it and learned something. In the next video, we'll see how to maintain the properties of heap when we insert or delete a node from a heap. So please make sure to subscribe this channel and hit the bell icon. And please like this video as well. And if you want to learn about any topics in computer science, please make sure to leave a comment below. Thanks for watching.